It's just in case an expert.
Hello, everybody. How are you doing? Hello, good to see you. Thank you for being cheery. Okay, so administratively, if you go to Canvas, what you'll see is that in addition to the exam number 1 grade, it now allows you to upload a file to that assignment. Okay, so if you would like to suggest corrections in your grading, you're welcome to do so. And the solutions are available on the other website, not the Canvas website. So you can take a look at the solutions, take a look at what you've got, and if you've got issues, you write a 1-page or the first page of your suggested corrections are your explanations for what you think was unjustly rewarded, and then, of course, attached PDF of the rest of the exam. Yes?
So we should come to your office hours and do that?
You're welcome to come to my office hours, yes.
Okay.
There are 130 of you though, 136. So, right. So this is the message. This is the process. Yes.
When would the last possibility be?
If you look on Canvas, I believe November 16th is the deadline for this, last possible. And that's because the next exam is on the 21st. So this has to be, you have to get this all done before the Yes. You should have the points that were awarded on the exam. And you have the points rewarded, you have solutions. That is what we're going to give you. Okay. Where? On the solutions are on the website. On the engineering-content.com website. Where are all the other exams that you've been looking at for the past 5 weeks?
In the back of my mind.
On the same page.
I see them when I go to my house.
Okay? All right. So, today, we get to switch gears a little bit, all right? And we get to talk about thin-walled pressure vessels. Okay? What are some of your what are some of your favorite thin-walled pressure vessels? Fuselage. Oh, you looked ahead.
Yeah.
Good. Yes, a fuselage on an airplane. That's a good one. Yes. A balloon. That's another good one. Yes. What are some others? Yes. Submarine. Yes. Yes. Some catastrophic stuff can happen, right? If you're not careful. Now, the issue with a submarine, what's the difference between the fuselage on an airplane and the fuselage on a submarine? Okay, yeah, sure, Kevin.
The fuselage on an airplane, I think, is in tension, and the fuselage and the submarine is in compression.
Correct, yeah, so the pressure is higher on the inside of the fuselage of an airplane. Why? Why?
Less pressure in the air.
Right, and why?
Airplane has to press out.
Airplane what?
Airplane has to go out because the
But
air.
why?
mountains
Why?
are going in.
Why?
I need to breathe air.
Yeah, you need to breathe, right? That's pressurized.
That's crazy. I don't
It's
have to.
pressurized.
You don't have to.
It's pressurized because we can't breathe up there, okay? And a submarine, of course, is supporting, it can be supporting an extreme load, okay, from the outside, and the pressure inside would be less, okay? All right, so, you know, your propane fuel tank, it's not summer anymore, but if you have one of those, right, it's pressurized. The hydrogen tanks now being proposed for some vehicles, all right, that's another one. You go down, or you go up from here to 95, and you see those enormous tanks, right? Okay, also pressurized, yes.
I have a question. For the submarine, it's usually have
To what?
but they have two pressure vessels, like they have like the one that people live in and that's one for outside.
It could depend on the design, yeah. I mean, you still typically, I mean, you have windows, right? Windows are a problem, right? And in fact, if you, yeah, windows are a problem, let's put it that way, right? So there's decent engineering that has to be done to make sure that they don't break, okay? And I think, I was just watching, what was I watching? Like one of the first Earth shots, right? They were saying they had, I think, already sent astronauts up, but no one had seen the Earth, right? And then they made windows, and it was, okay, fact check me on that. I was reading this recently somewhere. I can't remember. Yeah, but with Apollo, they had figured it out. By Apollo, they had figured it out, okay? So, there are two equations that are key for two equations, two different types of geometries that we're going to be using. And if you've taken a look, all right, one is for what we call cylindrical pressure vessels. Yes. Oh, that's beautiful, isn't it? There are no mistakes, no errors.
You're perfect.
Far from it. Is perfection the absence of mistakes? You think? Is a blank piece of paper that has no writing on it for an exam perfect? All right. I'm not very good at philosophy, obviously. Okay. So, P on the inside, pressure, okay? And there, you look at the derivations, right? For those of you who want to know, it's not a very complicated derivation, all right, but I'm going to skip it for now. But it's definitely in the notes, in the videos, how we go from the stress in the walls to between the pressure on the inside of the vessel and the stress in the walls, okay? And what you're going to see is that we have two stresses that we're interested in. And we're not talking about the stresses on this face or this face. We're talking about stresses along the wall, the longitudinal wall, okay? There is something we call hoop stress, okay? And this one we might call sigma 1. And there's something we call longitudinal stress. I don't want to use that color. Let's use this color. And we might call this sigma 2, all right? Sigma 1 is purposely drawn larger than sigma 2 in this poor diagram, and that's because it is larger, all right? So if you get confused and you're like, oh, I don't know which stress is the one that I gotta be worried about, it's the one in the hoop direction. So if you're thinking hula hoop, right, it's the one in the circumferential direction. That we call hoop stress. So sigma 1 we call hoop stress. Okay? And sigma 2 we call longitudinal stress. And the memorization is whoop, there it is. All right? There you go. If you look in the notes, sigma 1 is going to be PR over T, where R is the radius, okay, not the diameter. Why do I say that? Because I have done this so many times the wrong way. T is the thickness, all right? And what we're assuming is that the radius is at least 10 times the thickness, okay? So T is the thickness of the wall. Okay, and we're assuming that R is greater than 10 times T. Okay, so that's pressure, radius, thickness. The longitudinal stress, okay, is half. Okay? Now, I said that we only care about the hoop stress. We actually very much care about both, especially when we start thinking about shear stresses that we're going to have in this wall. Okay? So you can, for now, just compartmentalize the idea that the hoop stress is the dominant one, but they're both going to be very important when we start looking at transformations and the idea of what is the effective stress, okay, that's going to be causing failure. Now, the other type of object that we look at for these problems is a sphere. Okay, this is my really bad sphere. Sphere. Okay, you know what I mean. Okay, so we got pressure on the inside. Okay, and in this case, something interesting happens. It doesn't matter what orientation of an element I have on the surface. It does not matter. The stresses are equal in any direction. So I can rotate that element any direction on the surface of a sphere, and they are going to be sigma 2. Okay? And that's how Hibbler talks about it. I think this is the convention that Hibbler uses. Sigma 1 is the hoop stress, sigma 2 is the longitudinal stress in cylindrical pressure vessels, or is the stress in the wall of a sphere. Okay? So what does this mean? It means that a sphere is a really nice geometry, right? Because the stress is half, right? The maximum stress is half what it is in the longitudinal direction. So why don't we use, so why do we even use cylindrical pressure vessels? Yes, Chris? I didn't forget your name this time.
Appreciate it.
Yes.
Welding it, sphere is very difficult.
Yeah. It's very difficult to bend metal in two directions, as it turns out. Okay? Sheet metal in one direction, not a big deal. But doing it in two, not so fun, right? So that's one. So fabrication also, yes. Yeah, right. Okay, how many times do you go down the highway and see, a big fuel truck with a bunch of spheres on the back? Not really, right? That's not a very efficient use of our square or rectangular lives, right? When you think about how you pack things in boxes, right? You're not gonna, unless you're buying a certain type of juice that has a pomegranate in it, right? Most of those things are bottles, okay? And actually, so are you packaging engineers? Any packaging engineers? No packaging? We do have a packaging engineering program here in our department, right? I'm not supposed to be advertising that?
Because you're kind of aerospace.
Okay, so the director of aerospace?
Yeah.
No! You should follow your passion. If it's packaging engineering, go for it. Alright, so.
Can I ask you a serious question?
Yeah.
What would you do as a post?
Wakes up and says, I want to be a
Packages?
Oh, no, guys. Okay, whoa. This is not an opportunity to knock on our fellow packaging engineers, alright? So you get to focus on the package, alright? Wait a second. We have no appreciation for packages in our lives? You have a lot of appreciation? Yes, I mean, everything you have comes in a package. Your phone comes in a package. Your whatever, it all comes in a package, right? Huh? Not a car? A car does not come in a package. But there were crates somewhere. I think, maybe not though, actually. There's not these crates. Yeah, no. But anyway, so the packaging engineer has to make sure that the package doesn't fail, and it also has to convey, an artistic appeal. Alright? And it has to be a marketing tool. So it's like all these functional requirements packaged in one package. Alright, so yeah, so the reason I asked about packaging issues is because we had this nice packaging banquet, and one of the keynote speaker was talking about how some companies have actually been trying to make square bottles for different products. Because we live in a rectangular world, right? If you're going to pack a bunch of liquid in a box, why not make it fit the box? Right? That's what milk cartons are often, right? Okay. And what are milk cartons? You remember from the first class we talked about different materials? What are many milk cartons made of? What? That's a good joke. That's a good joke. That's good. Okay. What are many milk jugs made of? Okay, so some we're seeing a lot more on the paper front, right? So polymer coating. And what are the other ones often made of? Okay, which plastic? It's not polyester. Polyester is that soda bottle over there. Okay, that clear, that's polyester. That Fanta one he was holding that up as a package, that Fanta bottle. You hold your Fanta bottle, you want to stop, sorry. That is polyester, PET. Okay? Yes, any others? Okay, well, it could be somewhat thermoformed, yes, and weld it together. What's it made of, though? It thermoform a lot of plastics. Huh? Oh, PVC, no, not PVC. No, PVC is really cheap, all right? And we do use it for liquids, all right? And it's pretty lightweight, but we don't use it for that. And don't burn PVC because it has chlorine in it. That's not a good thing, all right? That's a good guess, though. PVC is your pipe. Yes. Have you used the internet?
No, absolutely not.
No, it's high density polyethylene. Okay? And polyethylene is an interesting material because it's actually very resistant to solvents. Okay, we digress. So, but that's another example of a pressure vessel. Okay? Because you've got a body of liquid sitting in the container, right? And where's the pressure the highest? At the bottom, and that's kind of where you have PGH, or rho GH. Okay, let's do a little bit of work here because I think there's some cool things. So we now know how to calculate stress. All right. How do we go about calculating strain? All right, so we have formulas now. We have nice formulas. What about strain? Okay. Okay, so that could be, yeah. Okay, so you could think about it in terms of a change in diameter, and we're going to relate it. I'm thinking about the wall of the material. Yes.
Is there a way to use the hoop modules?
The what?
The hoop modules. Like instead of an elastic modulus for axial or beams, is there maybe a modulus for spherical objects?
Okay, interesting question. So we're not going to introduce a new modulus. Okay, what we are going to do is use the elastic modulus, right? So let's back it up. I've been saying let's take an element on the surface of a vessel. Hey guys, right now we're not working together. Okay, so let's. All right, thanks. You will have time to work together. I highly encourage that. Okay, but right now we're trying to do something together. Okay, or doing this together. We're trying to connect. All right, so take an element on the surface of a vessel. What does it look like? It looks like what we just said. All right, let's just say that we have, this is the hoop direction, and this is the longitudinal direction. All right? So, with this, how do we go about figuring out how much strain this is under? Yes?
Young modulus, to the normal stress, which is the hoop or whichever one we're working on, divided by the actual.
Okay. All right. So, you guys remember these?
Oh, the Matrix.
That's what.
Okay? It's not a big deal. It's really not, okay? I need to tell you something about what's happening normal to this element. Okay, and you can look in the notes, we talk about it, alright? So in the Z, let's say that we have, let's just call this one, we'll call this one sigma x, and we'll call this one sigma y, alright? So those two, right, we know are PR over T and PR over 2T, alright, or PR over 2T and PR over T, whatever. Okay? They have pretty significant values, as it turns out. Okay? And with a very thin wall, okay, the pressure right on the surface of that wall is pretty low. It's pretty much atmospheric. And the pressure on the inside of that surface is P. But look, P is P. And this is PR over T and PR over 2T. Remember that R is 10 times, it's 10 times T. Okay? So P ends up being like 1/10 of whatever stresses that we're going to be calling here in the longitudinal and the hoop directions. Okay, so what we say is that sigma z is about 0. Okay, so sigma z is about 0, and that means that we can kind of forget about this contribution here in the bottom. Okay, what does this mean though for the other ones? Well, you could still, all right, so sigma x or epsilon x, right? Okay. Okay. Okay, I think I did that right. Okay. Yes, I think I did that right, except this is not right. No one told me that. There, that's why. It's like, that's okay, so we can calculate the strain using these material property relationships that we've discussed previously. Okay? Now, what happens if we have example 15.3? okay, where we have a ring about a bladder. Oops. There we go. Okay. What happens here? Oops, that was the wrong key press. Well, in this case, we have an opportunity to think about how strain is related to the change in radius, like you were suggesting earlier, okay? And it's going to be related to what we have with the following, right? So 2 pi r, right, this is a circumference. Okay. If I'm interested, so I'm wrapping this around. That's the circumference, whoop-de-doo, right? If I think about the strain, okay, that I have here, so how much does this is going to expand a little bit, right? It's going to expand a little bit if I have pressure on the inside. So it changes, all right? What happens, the circumference gets larger. So if I say that initially the circumference is 2 pi r initial, all right? We can talk about a change in circumference, a delta L, okay, which would be 2 pi times the delta r, right? That's, so if I change the radius a little bit, that's how much the length of this perimeter is going to change. And this delta L, right, can be related to the strain, okay, that we have and the initial length, right? That's the definition of strain, of normal strain. So, if we're interested, okay, in how much, okay, this is changing, okay, so now we say, okay, I want to know, I can equate, right, these two to each other. Okay, so I have 2 pi delta r is equal to epsilon times the initial length, or the initial circumference. Okay, we can say that if we can figure out what this is, okay, we'll be in good shape. All right, and epsilon can be roughly estimated as, well, let's do this first. Sigma, let's say we're in the circumferential direction, that means we're in the hoop. So sigma hoop is going to be equal to PR over T, and that in that direction, right, what we're going to have is that the epsilon is equal to 1 over E, right, times like this. Okay. Now, if this is a ring on a bladder, okay, this is something that may be a little bit weirdo, okay? Why do we put a ring on the bladder? Why do you think they're trying to make it on a ring? Why are they trying to make it a ring under the bladder? Why? Huh? Okay, yeah, so it's reinforcing it. Yeah, okay. Yes? Yeah, so it's like maybe the bladder is the water sealant, right? That's waterproof, okay, and you put something around it, okay? So those are very good practical reasons. In this case, what is the longitudinal stress in the ring? Not the bladder, but in the ring. It's actually 0. Okay? Because if you go back to the derivation, okay, which you can, there are no end caps. The end caps are what cause there to be longitudinal stress. When we put this ring around it, there's no longitudinal stress. There's no force in the longitudinal direction. Okay, so this is kind of a subtle point. So because it's a ring, because there are not capped ends on the ring. It's just a nice open looking ring. Oh, that's horrible. Okay. Anyway. Okay. So you don't have to worry about this one. So what does this mean? This means we get a free lunch. The epsilon is just equal to 1 over E sigma h. It's not free. It's just less painful. It's like you're only getting the green peas and not the spinach too, or something like this. Okay? So now, what do? We can say, well, this epsilon, all right, I can figure out is 1 over E times this, so I'm just going to bring this down. Okay, it's just going to be 1 over E times PR over T. Okay, and so now we can figure out what the change in radius is. The change in radius is just going to be PR, okay, right, yeah, there we go. It's going to be PR over 2 pi E T times Li, which was 2 pi R. So this is going to be equal to PR squared over 2E. ET. Yes, that's right. Okay. Any questions on that? Okay, this is a little bit of mental gymnastics, a little bit, at least for me. But that's great. And T, okay, if it's thin, T can sometimes be considered R naught minus Ri. Okay, so the outer radius minus the inner radius. Okay, this is an interesting formula. This PR squared over ET, or PR squared, okay, because it gives us some idea about how the radius is related to the internal pressure, okay, or the change in radius is related to that. Now, there's a problem that you all will get to encounter. Let's see. Okay, it's number 4. So I want to talk about this a little bit. Okay. Okay. So in this case, what you have, all right, is a cylinder surrounding a cylinder. So imagine there's one cylinder, and then there's another cylinder, around it, okay? And then there's an internal pressure, okay? And the question is, what is the hoop stress in the outer cylinder? Okay. So this is a little bit of a tricky one, all right? We're going to define some type of Ri, or R1 we'll call it for the inner, and we're going to call it R2 for the outer, okay? We just spent some time talking about how we can relate changes in diameter, okay, to the internal pressure times the radius squared over ET. Okay? Remember we have our tenets, we have our tenets of geometric compatibility, equilibrium, right, and constitutive equations, okay? Let's think about geometric compatibility first. In this case, we'll call this R1, okay? And we'll call the other one about it R2, okay? And sometimes for these radii, right, you could say, oh, I really want to do the inside one. That's fine. A lot of times they do the inside one for R1 and the inside one for R2, right? Because these thicknesses are all small. For doing these types of problems, these thicknesses are small, so whether you pick the outer or the inner, it doesn't matter too much. Guess what? These are connected to each other. Okay, so what we're going to say is that the delta R1 is equal to the delta R2, right? They're thin, they're connected, and so they're going to move with each other. All right, that sounds like other types of geometric compatibility we've used in the past. For equilibrium, we need to think a little bit hard here. There's an internal pressure. Okay, we'll call this P1 inside. Right? And then we can think of there's actually some type of pressure acting down on me. Like Freddie Mercury and David Bowie would say. Okay? So there's a contact pressure, we'll call it PC. Okay? That pressure is being applied, right, by the outer ring. Right? There, that pressure is acting actually on this ring. And so if we look at a slice, wouldn't it be nice, right? What we have is an interesting balance, okay, between the PC acting on this one, this is the outer one, okay, and on the inner. So we could say that we have some PC pushing down here, and we have some PC pushing out here, okay, and it's in equilibrium, PC. That's the contact between these two. So, how would you describe, we have this equation, PR squared over ET, okay? How would we describe the change in radius delta R1? And constitutive equations, we'll just say that we have hoop stress is going to be PR over T. So my question is, what is delta R1 based on what you see here? Right here. What is it? What is it? What is delta R1? Put in the right variables. This is your homework question, so we're doing it together. What are you gonna guess? What is delta R1 in terms of that PR squared over ET? Yes, Paul. Yes. All right. It's going to be P1 minus PC. Okay. And then, fine, we can use R. Well, okay, you keep going. Keep going. You keep going. You keep going. You keep going, guy. Yes. Yeah, I mean, it could be like R2 minus R1, but let's just call it ET1. Okay, so the thickness of the first ring. Good. You got it. You got it. All right? That's the hardest part of the whole problem, just understanding that bit. Does everyone understand why that pressure is the gauge pressure, okay, that we're interested in? It's the difference between, so like in the airplane, when you do the fuselage problem, right? Where we have a pressure that we're pumping up to, right? And then you have some pressure on the outside, right? You still have an atmosphere. It's that difference, it's the delta P that we actually care about. Okay. So, but often we don't, because if you're cranking up, something on a pressure vessel to, 100 atmospheres, well, 1 atmosphere is not a big deal, right? Which is the surrounding environment. Okay, so so what is delta R2 now?
PC,
Yes, PC.
R2 squared
Yep,
over ET2.
you got it. Okay. So now, all right, we can figure out. Okay, it depends on what you're asked, right? But we can now say we have this nice big equation. Okay. And if they ask for the hoop stress, what is the hoop stress in the outer cylinder? Well, there it is. What is actually, we don't know what it is. The hoop stress in the outer cylinder. In outer cylinder, what is that? What is that? That's a simple one.
PC times R over T.
Yeah. Okay. Or PCR2 over T2, right? Yeah. Okay. So what's the dealio? We had to figure out like all these parameters, P, is given. E is given. You know, you can measure the thicknesses. You can measure the radii. The thing that you don't know is what is unknown here? Yeah. PC. So we have to solve for PC and then stick it in here. And that's the hoop stress in the outer cylinder. Okay? So that's the hardest problem on the problem set. Okay? Any questions? Great. So go ahead and start working on the problems, please. Whoa. All right, well, that we'll go with that. We'll go with that. No, it was me. But I didn't think it was a bad choice, but I guess it was a bad choice. Okay. Please ask questions during this time. Look, a lot of you should be done with the assignment that's due today. If not, that's okay. Actually, there was a question on both of them. But this assignment, free up your weekend. This assignment is not that bad. This one is not that bad. I mean, it's a little bad, but not that bad. Free up your weekend. Finish it now, or get started on it. Okay? Yes. Huh? For which problem? Okay, so there was a question. So you guys be loud. You keep working. And for those of you who are interested in question number 2 from session 14, all right, let's talk about it. Okay?
Excuse me, real quick.
Yes.
My phone's dead, so I can't take a picture of the.
Use your laptop or use your friends. Or find someone. Find someone.
No, okay.
Okay? You can find someone. Be resourceful. Ask someone for a favor.
I'm not trying that.
Huh?
Can I just email you?
No, because I prefer, because it takes me time. I prefer you get it. I prefer you figure out the solution now.
That's my bad, sorry.
Yes. Use your laptop if you have to.
Yeah, sure.
Use your laptop. Use your resources. Please do not send me a message saying you couldn't do this. There are other people in the class. Okay, so there was a question on session 14.
If it is the case, right? Because if there is atmospheric pressure outside of the second break, and does the radius always move the thickness of the even when it's like after, like no matter
Okay.
after the change. So for instance, if there's a problem,
Sorry, this is fine.
Yeah, that's fine. That's fine.
if there's a case where you know.
Okay, so session 14, question 2.
Do you have to take that into account? Do radius have to do radius plus delta? Like, does radius always take into account radius? Right. Right.
Okay, so we want the average shear stress.
Better?
Oh, shit.
Be half the maximum bending stress. Okay?
And then I think I'm gonna be
So the average shear stress
I have an interview next week.
is force
That makes sense.
over 2A. And the bending stress is negative my over I. Okay? So, what we need to think about, okay, if we have base B, height H, all right, and length L,
Oh, yo.
okay, we're going to work on this problem. So the area, right, so what are we, remember what we talked about here? When we think about these double shears, we're thinking about the length between here. Okay, and the area is going to be that rectangle there. Okay, and in this case, this would be the length here. Okay, so if we're thinking about the cross section, okay, we would say that we have a height in this direction, and we have a base in this direction. Okay, and this is the beam in between. Okay, and here what we're saying is that we've already done this previously, all right, but the force, and this is double shear, so I should be careful. Okay, I have to be careful. This is double shear, so that the tau average is going to be 4 over F over 2 area, which is just F over 2BH. Okay? Now, what is the bending stress? Well, we need to figure out the moment. And if you go back, right, we figured out the moment previously. It maxed out, okay, at PL over 4. Right, so M max, let's do it this way. M max, all right, and when we were doing this, okay, over Y max, right, which is, I'll go through this, over I, all right. So if you remember this problem that we did, right, this is for the double shear. What we said for double shear, the moment diagram looks something like this. Okay, and this comes out at PL over 4. Okay? And this is L, and that's the x direction. Right, and this is L over 2. Okay, so M max is PL over 4.
No, I know.
Y max, okay, this is going to be H over 2. Okay, because this is the height of it, right? And so this is, in this case, this is the Y direction. Okay, and I is just going to be BH cubed over 12. All right, is this making sense? Graham, you're still here? Okay, so for this one, what we have to do is we say we want the shear stress to be half of the maximum bending stress. So what we actually want is we want tau av to be equal to 1/2 sigma max. Does that make sense? Okay, so in this case, we're going to have F over 2A is equal to, or 2BH. All right, and we have this times equal 1/2 times in brackets minus PL over 4, okay? Or we could say, actually, this we're going to use, we did P here. It's really F, all right? Anyway, we can say that this P is equal to F. Okay, so we're going to say this is F L over 4, okay? This is going to be H over 2, or it could be minus H over 2, whatever, right, to get rid of the negative, all over BH cubed over 12. And then what do? We solve, we cancel out relationships, okay, and we get an expression, all right, get an expression for L. Okay? That's how we go about it. All right? Other questions? Was there another question? Yes. How do you equal? Is that how you say it?
Sure.
How do you say it?
Better
Equal. Sorry. Okay. Better equal. What's that?
I had a question for one of the examples.
Okay. Yeah. 15.2. Yeah.
Like the radial stress is 0.
The radial stress is going to be approximately 0.
So it's just much less.
It's much less than the other.
So it's like the same explanation.
Yes. Yeah. So the same thing. Yeah. I mean, it's the same thing. The sigma z we say is 100%. Someone else. I think there was a question on. They may be gone now, but hopefully not. There was a question about how to hack.
Click on the same thing.
This one? Was this the one? People were having a question about? Did anyone have a question? Does anybody want me to go through this or not?
Yeah, I would.
Yes? Okay. So the question was, this is session 14.
Sigma y should be the root stress of sigma.
Okay, so there's a question of how do I find, oops, I'm going some distance from the right, D, correct? And the question is, what is the transverse shear stress at the specified location, right? And we have, we'll say we have something like, we'll call it an x2. We'll say x2 is equal to d, and we'll say that we have, this is a little bit tricky, but let's call it y prime, okay? And height y prime. I understand that this is saying y here, okay? Let's just forget that for a second. Okay. So the question is, how do you go about figuring out what the shear force, okay, is at a given location from the right end? Okay? And here we are. We're using the convention for V and M, okay, as we have here, and we're going a distance D from the right. In this scenario, was there a question? Are we good? We're still trying to find the transverse shear stress, right? So we have tau is equal to VQ over IT. Okay? So in this case, to find V, the easiest way to do it is just to do equilibrium right here. And what we do is we say, okay, there's some F effective acting some D over 2 away. This F effective is W naught D, and that's what we have for V. M is just equal to 0, so V is equal to W naught D. That's it. Okay? Q is a little bit tricky. Okay? Q is found by thinking about, actually, let me do it this way. Some distance above the neutral axis. Okay? In this case, we've got to think about the A prime. Okay? This is A prime. Okay? And actually, that's big A prime, I guess you could say. And I think the way we looked at this cross section, it had equal sides, if I'm not mistaken. So let's call this side little a, and we'll call, now we got to figure out what the area A prime is. Well, and this area, this is A as well, right? So what is A prime? Anyone want to tell me? What is A prime equal to?
Would it be A times A over 4?
Okay, so not A over 4 necessarily, because we don't know how high we are. I didn't say that we halved it, right? So now tell me what it is.
A times A minus Y prime over 2. Something like that.
Right. So this is going to be A times A over 2. Sorry, see, I did it wrong. Minus Y prime. Okay? Now, how do we figure out where the vertical length is to the centroid of A prime? Right? How do we figure that one out? Right? So now we need to figure out Y bar prime. Right? So what is Y bar prime? This one's a little bit confusing, right? So I'm going to say first, I know it's some Y prime. Whoops.
Wouldn't it be A over 2 minus Y prime over 2?
Right. So Y prime plus, okay. I'm going to say, well, it's A over 2 minus Y prime all divided by 2, essentially, right? So it's going to be A over 2 minus Y prime all divided by 2, because it's halfway in between there, all right? And so that's how you figure out Q. Q is just the Y bar prime times A prime. What is I?
BHQ.
Yeah, and in this case,
Would be A to the minus Y.
good. And what is T? Yeah, and that's how you do it. That's how you solve this problem. Okay. Other questions? Other questions about how you go about anything on these assignments or concepts? Okay, can you get it? Okay, good. All right, so all right, so there was a question on the collar, the double collar, the two ring problem. So I'll try to explain it again. Okay? We have, so do you have a question about this equation? Is this equation okay with you? That one's okay? All right. This one's okay, presumably? That's okay? All right. So really it comes down to geometric compatibility and equilibrium. Okay? And what we're interested in, you know this is all available, right? Everything here is all available. Just it's all available. It's the notes, right? If you click on the notes, just so you don't. So all my yeah, everything we do is available. All right. All right. So just what we have here is geometric compatibility, right? So how the inner ring, how the radius and the diameter of the inner ring changes with the inner diameter and radius of the second ring, the outer one, right? That they're going to be following each other. They're connected to each other. Okay? And then we have equilibrium. So there's a pressure, right? So there's essentially a pressure of the outer ring trying to constrain the inner ring. And then there's a reaction pressure and set of forces that are going from the inner ring, and they're exerting their pressure on the outer ring. Those two pressures have to be the same. And that's the contact pressure, right? It's like if I have one fist and I have another fist and they're fighting against each other, right? They're going to have equal and opposite forces, but if it's the same surface area, which it is, it's also equal and opposite pressures. Okay? So that's equilibrium, and these are geometric compatibility. So if we have this equation, all right, which is not, this is, let me just put, this is, just so people don't get confused. This is the question that goes all the way down here. This is not, this is from, previous example. Previous. Okay, so we can use the change, if we know these relationships, we can use these delta R's for the inner and the outer together, right? And so what we had to do, was it Paul? He's gone. But anyway, Paul helped us understand that the delta R1 can be thought of, or this equation can be thought of for the inner one as the difference in the pressure. There's an inside pressure and there's the contact pressure, and they're working against each other. And it's the net pressure, or the gauge pressure, that determines the amount of stress in the inner wall, and also the amount of strain in the inner wall, and the change in radius, okay, of the inner wall. And then for the outer one, it's just that contact pressure. Assuming that the pressure of the atmosphere is pretty small, it's just the contact pressure. Okay?
Professor?
Yes.
What of the other problem? The previous one?
The previous one? What about it?
No, he just wants to know that.
Oh, the previous one? This one?
No.
Oh, the distributed load one. Okay, yeah, the distributed load one, yeah. Okay. This one? Yeah. Okay. Again, all these are available on the website. Everything you see here, just so that people, I'll just pull it up so people can see. We're moving along. We're over halfway through the course, folks. Is that good? So if you go down to the notes. It's not here. Okay, it's in the, that's my fault. But it's the same thing. Oh, I proved myself wrong. Yeah, fall in class on office hour notes. No. Okay, I don't want more storage. Okay. If you go down, we're in 14 and 15. And there it is. You can also print from this.
This
Yes.
might be a stupid question, but what's that T in the bottom of the sheet formula?
The T?
Yeah.
Okay, so this T is what we refer to as the thickness.
Okay.
Okay, and it's this direction.
Yeah.
Not
the height.
this, not the height.
Okay.
T and H are not the same here.
Okay.
Okay, so it's the thick. It's what I usually thought of when we talk about BH cubed. It's like the
Yeah.
base.
Okay.
So B and T are like the same.
So B and T are the same.
Yeah.
Okay.
Yeah. Okay. Good question. Other questions? All right. Yes,
Just
Chris.
double check. R1 is, R2 is just the R1 plus the T.
Okay. Good question. Good question. So, yes. Well, they often are a little bit ambiguous. Okay. So. Someone might approach this problem, say there's the R inner, the R interface, and the R outer. Okay, because which problem are you talking about?
No, it's just like the diagram you were doing earlier.
For the 2 ring,
Yeah, the one you got excited.
I got excited. Okay, maybe it's going slow there. Let's go over here.
Yeah, that one.
Okay, so R1, I'm saying is either to the inside of the inner ring or the outside of the inner ring. Because the thickness is small. T1 is small, right? So if I have, now, that T is significant because it plays a role in the denominator, right? So that thickness makes a big deal for the PR over 2T or PR over T, right? It has a huge impact, okay? But for the numerator, it doesn't matter, right? If I did like R1, because R1's 10 times the thickness, right? So if I said that R1 is the inner or R1 is the outer, right? T is really small compared to R or R1, so it doesn't really matter. Okay, but yes, you could say that often what they'll say is that R1 plus the thickness, but usually they often say R1 is the inner one. Okay? But it doesn't matter. It doesn't really matter. A more conservative approach, if you're worried about hoop stress, is actually to use the outer one, because this is slightly larger. But it doesn't really matter. Okay, and then R2 is what we'll call the radius of the outer ring. Okay? And that could be, again, on the inside interface or on the outside interface. It shouldn't matter too much. Because, again, that thickness is very small relative to the radius. You didn't like that
How
answer.
many rings are we dealing with here?
Well, you have a ring on the inside, right? And then you have another ring, right? So
So like
there's
two
a ring.
donuts, two like a.
It's like a donut around a donut, yes, like this, right? So you have the radius of the inside of the inner donut, and you have then the radius of the interface, and then you have a radius of the outer donut. Good. Any other questions?